Myself, Ketanam Patel from Mahatma Gandhi Institute of Technical Education and Research Center, Navsari, Electrical Engineering Department. Subject is Electromagnetic Field, 4th semester, 2nd year. Today we will discuss about chapter number 1, Review of Vector Analysis. Now, syllabus content. First is introduction, second one is scalars and vectors, third one is unit vector, fourth one is vector addition and subtraction, fifth is position and distance vectors, sixth is dot product and cross product, seven is scalar triple product. Now, introductions. Vector analysis, a branch of mathematics that deals with quantities that have both magnitude and direction. Some physical and geometric quantities called scalars can be fully defined by specifying their magnitude in suitable units of measure. Thus, mass can be expressed in grams, temperature in degree on some scale, and time in seconds. Now, it is possible to study electric and magnetic field without the use of vector, as most of you may have done in basic physics course, but the use of vector in the study of electromagnetic field theory saves the time and provides economy of thought. The scalars can be represented graphically by points on some numerical scale such as a clock or thermometer. There also are quantities called vectors that require the specification of direction as well as magnitude. Velocity, force and displacement are examples of vector. In addition, the vector form gives a clear understanding of physical law which is described by mathematics. For the reason, vector quantity can be represented graphically by a direct line segment symbolized by an arrow pointing in the direction of the vector quantity, with the length of the segment representing the magnitude of the vector. At the observation point, the field which we observe may not be because of single source. The total field at the point is obtained by adding field due to different sources. This additions is not normal additions, it is a vector additions. If the direction of fields are opposite, it is vector subtraction. Thus, the vector algebra is introduced early in the text. The unit deals with vector functions and extends the difference calculus to these vector functions. Finally, discuss physical meaning of three important concepts, namely the gradient, divergent and curl. Okay. Next, now scalar and vectors. Now, what is scalar? A scalar, a quantity that has only magnitude and algebraic sign, is called scalar or scalar quantity. For example, mass, density, pressure, volume, etc. are the scalar quantities. Now, vector. What is vector? Vector is a directed line, a line having both magnitude and direction. The vector has a starting point and end point. Direction is A to B, like. Okay. So, this is called vector. This vector is written by AB. Okay. The first letter AB indicates to start or tail, and the second letter is the end or head of the vector. The arrow or bar over the head of the letter is used to indicate vector. Okay. Here this is a scalar product. We can also say dot product of two vectors A and B is defined as the A bar or arrow of A into B is equal to A B cos theta. Okay. Where 0 less than equal to theta less than equal to pi. Here theta is the angle between A and B. Note that A dot P is a scalar quantity. Here these are the different types of general properties of scalar product. Here first is A dot B equal to B dot E. This is the cumulative law. Second one is A dot in bracket B plus C. So, A dot in bracket B plus C equal to A dot B. Okay, this is the A dot B plus A dot C. Third one is I into I equal to J into J is equal to K into K equal to 1. Where I into J equal to J into K equal to K into I equal to 0. So, same quantity is equal to 1 and opposite quantity is equal to 0. Fourth one is if A equal to A1 into I plus A2 into J plus A3 into K and B equal to B1 into I plus B2 into J plus B3 into K, then the both equations we can calculate with the help of multiply. The A dot B equal to A1 into B1 plus A2 into B2 plus A3 into B3, and the same A into A is equal to A square. So, this is equal to A1 square plus A2 square plus A3 square. And next is A dot magnitude of A into B less than equal to magnitude of A bar and into dot magnitude of B bar. Now, 6 is A dot B is a independent of coordinate systems. Okay, next, typical applications of scalar product. If A is not equal to 0, B is not equal to 0 and A dot and B is equal to 0, then A and B will be perpendicular. Now, these are the general properties of the vector product. Okay. If A and B are parallel or antiparallel, means collinear, then A cross B equal to 0. Here A cross A equal to 0, I cross I equal to 0, J cross J equal to 0 and K cross K equal to 0. Second one is A cross B equal to minus B cross A. This is the anti-commutative law. Third one is A cross in bracket B plus C. So, this is equal to A cross B plus A cross C. Fourth one is I plus J equal to K, J cross K equal to I, K cross I equal to J, while J cross I is equal to minus K, K cross J is equal to minus I and I cross K equal to minus J. Okay. Next is if A bar equal to A into A1 into I plus A2 into J plus A3 into K and B equal to B1 into I plus B2 equal to B2 into J plus B3 into K. So, this vector product of two vectors A into B as a determinant is represented as a given below. A cross B equal to in magnitude I j k A1 A2 A3 and B1 B2 B3. And this is a solution. A cross B equal to first of I, and this is a cross marks A2 into B3 minus A3 into B2 minus second one is minus J is equal to A1 into B3 minus A3 into B1. Then after third one is K plus K equal to A1 into B2 minus A2 into B1. So, these are the A cross B. Now, typical applications of vector product. Area of the parallelogram with sides A and B is equal to in magnitude in bracket A cross B. Okay. Now, unit vector. Unit vector, this is the triangle. This is the area of the triangle with sides A and B is equal to 1/2 in magnitude A cross B. So, this x-axis is A, the triangle theta degree is B and the height is h. Okay. So, area equal to 1 half A into H, while H means B sin theta. So 1 half AB sin theta is equal to, in magnitude, 1 half A cross B. Second one is unit vector, that is perpendicular to the plane formed by A and B is given by n equal to plus or minus A cross B divided by, in magnitude, A cross B. Okay. Now, vector addition and subtraction. In unit vector, has a function to indicate the direction. Its magnitude is always unity, irrespective of the direction which it indicates and the coordinate systems under consideration. Thus, for any vector to indicate its direction, a unit vector can be used. Consider a unit vector like a, here it is AB. Okay. So, the direction of AB, this vector indicates the direction of OB, but its magnitude is unity. So, this vector can be represented completely as its magnitude and the direction as indicated by unit vector along its direction. In case if a vector is known, then the unit vector along the vector can be obtained by dividing the vector by its magnitude. Thus, unit vector can be this type of expresses. Okay. Now, vector addition and subtraction. This is nothing but multiplication by a scalar to a vector. Such a multiplication changes the magnitude or length of vector, but not its direction when its scalar is positive. Now, if two or more vectors are given, operations like additions or subtraction can be performed on them. Two vectors A bar and B bar. Okay. Let alpha is equal to scalar with which vector is to be multiplied. Then if alpha greater than 1, here first figure A greater than 1, then the magnitude of vector increases but direction remains same when multiplied. This is one figure. Second is figure B. If alpha less than 1, then the magnitude of the vector decreases but direction remains same when multiplied. And third one is in figure C. If alpha is minus 1, then the magnitude remains same but direction of the vector reverses when multiplied. So, these are the different types of way. Thus, if alpha is a negative, the magnitude of vector changes by a alpha times, while the directions become exactly opposite to the original vector after its multiplications. In additions and subtractions, the sum is another vector. C is a same plane. So, C equal to A plus B can be obtained graphically by two methods. First is by the parallelogram rule and second one is by the head to tail rule. First is addition of vector. Here consider the two coplanar vectors. As shown in figure, the vectors which lie in the same plane are called coplanar vectors. In coplanar vector, let us find the sum of these two vectors A and B shown in the figure. The procedure is to move one of the two vector plane parallel to itself at the tip of the other vectors. Thus, move A parallel to itself at the tip of B. Now, then join tip of A moved to the origin. Thus, the vector represents resultant which is the addition of the two vector A bar and B bar. So, this is just one in figure. Okay. Next is, let us denote this resultant as a C bar. This is the triangle. C bar, then C bar is equal to x-axis A bar and y-axis A bar and x-axis B bar. It must be remembered that the direction of C bar is the form of origin O to the tip of the vector moved. Another point which can be noticed that if B bar is moved parallel to itself at the tip of A bar, we get some resultant C bar. Thus the order of the addition is not important. The addition of vector obey the cumulative law. A bar plus B bar equal to B bar plus A bar. So this is the additions of vectors. Now another method of performing the additions of vector is the parallelogram rule. Okay, parallelogram rule and head to tail rule are the methods of addition and subtraction vectors. By using these two methods, not only two but any number of vectors can be added, obtain the resultant. For example, resultant these are considered for vectors as shown in figure. This can be added by shifting this vector one by one to tip of other vectors to complete the polygon. The vector joining origin O to the tip of the last shifted vector represent the same sum as shown in the figure. This method is called head to tail rule of additions of vectors. Once the coordinate systems are defined, then the vectors can be expressed in terms of the component along the axes of the coordinate systems. Then by adding the corresponding components of the vectors, the components of the resultant vector, which is the addition of the vectors, can be obtained. This method is explained after the coordinate systems are discussed. Here the different figure, first is 4 vector A bar, B bar, C bar and D bar. This is the different directions. And here second one is P figure, some of the 4 vectors A bar, B bar, C bar and D bar, and this is the resultant R, capital R. So capital R equal to A bar plus B bar plus C bar plus D bar. Okay, so these are the exact additions. The following basic law of algebra are obeyed by the vectors A bar, B bar and C bar. The law is first is cumulative, associative and distributive. In addition, cumulative A plus B equal to B plus A, and in multiplication by scalar, alpha A bar is equal to A bar into alpha. In associative, A plus in bracket B plus A bar and A plus B bar in bracket plus C bar, while multiplication by scalar, beta in bracket alpha into A bar equal to in bracket beta alpha into A bar, and in distributive, alpha in bracket A plus B is equal to alpha A bar plus alpha B bar, and in multiplication by scalar, alpha plus B bar into A bar is equal to alpha A bar plus B into A bar. So these are the different types of law. Now subtraction of vector. The subtraction of vector can be obtained from the rules of additions. If B is to be subtracted from A bar, then based on the addition it can be represented as C bar is equal to A bar plus in bracket minus B. Okay. In figure the vectors is A bar and B bar and origin is dot O, and in subtraction of vector B bar is opposite is minus B bar. Okay, and this vector A bar and B bar. So C bar is equal to A bar minus B bar. Okay, this is the reverse of sign of B bar. Reverse is direction by multiplying it with minus 1 and then add it to A bar to obtain the subtraction. Okay. Now next is position and distance vector. Position vector is a vector R is equal to x into x plus y to y plus z to z. Describe position of a point x, y, z relative to the origin whose coordinates are 0, 0, 0. Its magnitude is r equal to magnitude of r and root x square plus y square plus z square, and unit vector is in the direction of r is equal to r by r. So equation is equal to x into x plus y into y plus z into z, and divided by in root x square plus y square plus z square. So, position vector is next. Distance vectors. A distance vector routing protocol in a data network determines the best route for data packets based on distance. Distance vector routing protocols measure the distance by the number of routes a packet has to pass. One router counts as one hop. Some distance vector protocols also take into account network latency and other factors that influence traffic in a given route. To determine the best route across a network, routes on which the distance vector protocol is implemented exchange informations with the one another, usually routing tables plus hop counts for destinations networks and possibly other traffic informations. Distance vector routing protocols also require that a router informs its neighbors of network topology change periodically. Now, dot product and cross product. Dot product and cross product, like addition and subtraction and one more operations, can be performed on vectors. It is a multiplications. Vector can be multiplied by the two ways. First is dot product. Dot products also we can say scalar, while cross product we can say vectors. Now, we consider the first of two types of vector multiplications. The second type will be discussed in the following sections. Here there is a given two vectors A and B. The dot product or scalar product is defined as the product of the magnitude of A, the magnitude of B and the cosine of this smaller angle between them. So, A dot B is equal to magnitude of A dot magnitude of B and cos theta of angle between them A into B. The dot appears between the two vectors and should be made heavy of emphasis. The dot or scale product is a scalar, as one of the names implies, and it obeys the cumulative law. A dot B is equal to B dot A. The A means magnitude of A bar, capital B is equal to magnitude of B bar, and theta is equal to angle between A and B. For the sine of the angle does not affect the cosine term. The expression A dot B is read A dot B. Perhaps the most common applications of the dot product is in mechanics, where a constant force F applied over a straight displacement L does not amount of work F into L cos theta, which is more easily written F dot L. We might anticipate one of the results by pointing out that if the force vary along the path, integrations is necessary to find the total work, and the result becomes work equal to integration of F into dl. The definitions of the dot product can be used to find length of the projection of one vector on others. Now, the another example might be taken from the magnetic fields, a subject about which we shall have a lot more to say later. The total flux phi crossing a surface of area S is given by B into S. If the magnetic flux density B is the perpendicular to the surface and the uniform over it, we define the vector surface S as having the usual area for its magnitude and having a direction normal to the surface, avoiding for the moment the problem of which is the two possible normals to take. Here the total flux equations phi is equal to integration of P into ds. Okay. Now, the equations of A is equal to Ax, capital Ax into small ax plus capital A into y into small ay plus capital A into z equal to A into z. Now, second is B. B is equal to Bx into Ax plus By into Ay plus Bz into Ay. The dot product also obeys the distributive law, and therefore A dot B is the sum of 9 scalar terms, each involving the dot product of two unit vectors. Now since the angle between two different unit vectors, the Cartesian coordinate system is 90 degree, we then have ax into ay is equal to ay into ax into az is equal to az into ax, and ay into az is equal to az into ay equal to 0. So this is the Cartesian coordinate system. Now the remaining three terms involve the dot product of a unit vector with itself, which is a unity, giving a finally a dot b is equal to ax bx plus ay by plus az bz, which is an expression involving no angles. A vector dotted with itself is the magnitude square, or a dot a is equal to a square, or is equal to in magnitude of a square, and any unit vector dotted with itself, its unity. So a4 small a into capital A into small a into capital A is equal to 1. In next equation is capital B into A is equal to magnitude of B and magnitude of small a cos theta, and BA is equal to capital magnitude of B cos theta BA. The sign of the component is positive if 0 less than equal to theta BA less than equal to 90 degree, and negative when 90 degree less than equal to theta BA less than equal to 180 degree. Okay. So these are the different types of dot product equations. While the cross product in cross product, it is defined as a cross b equal to a cross b, or is equal to ab sin theta a. Okay, here it is equation of a into b is equal to an magnitude of a magnitude of b into sin theta ab. The cross sign does not mean simple multiplication, it is the cross product of two vectors. The term an indicates a normal unit vector, thus a cross b result in a vector. Okay, the determinant phase containing both, however, is most of our applications we shall be concerned with vectors defined at the same point. As an equation where an addition statement such as that given above is still required to explain the direction of the unit vector a into n. The subscript stands for normal. Okay. A reversing of the order vectors a and b results in a unit vector in the opposite directions, and we see that the cross product is not cumulative for b cross a equal to minus a cross b if the definitions of the cross product is applied to the unit. Now the simplest way they obtain the direction of a cross b is using the right hand rule. Okay. The first finger in the direction of the first vector, the second finger is the direction of second vector, and the thumb indicates the direction of the cross product. When the order of cross product is changed, instead of a cross b bar, if it is a b cross a, then right hand screw rule is advanced in downward directions, that is minus an, and because of this cumulative law does not apply to the cross product. So a cross b bar is equal to minus b cross a bar. Okay. So these are the simplest way of cross product. Now a simple example of the use of the two cross product may be taken from the geometry or trigonometry. To find the area of parallelogram, the product of the lengths of the two adjacent sides is multiplied by the sine of the angle between them. Using vector notations for the two sides, we then may express the scalar area as the magnitude of a cross b, or in magnitude a cross b. Now equations a cross b equal to ax bx, ax cross ax plus ax by, ax cross ay plus ax bz, a cross AX cross AZ plus AY BX AY into AX plus AY BY AY cross AY plus AY BZ AY cross AZ and plus AZ BX AZ cross AX plus AZ BY AZ cross AY plus AZ BZ AZ cross AZ. Now we have already found that AX cross AY is equal to AZ, AY into AY cross AZ is equal to AX and AZ cross AX is equal to AY. So the three remaining terms are 0 for the cross product of any vector with itself is 0 since the included angle is 0. So these results may be combined to give. Now A cross B equal to AYBZ minus AZBY into AX, AZ plus AZBX minus AX into BZ in bracket AY plus AXBY minus AYBX into AZ. So now final equations is A cross B is equal to in magnitude AX AY AZ in capital AX capital AY capital AZ and capital BX BY and BZ. In different cases the also different case vector product, first is A and B are parallel and cross product of unity vector are also applicable, and applications of different cross product like area of parallelogram and area of the triangle A, B and C. Now scalar triple product. In scalar triple product equations is A dot in bracket B cross C, while magnitude A1 A2 B3 B1 B2 B3 C1 C2 C3, where A is equal to AI A1I plus A2J plus A3K, where B equal to B1I plus B2J plus B3K and C is equal to C1I plus C2J plus C3K. Now A dot in bracket B cross C is a scalar quantity, okay, and A dot in bracket B cross C as a magnitude of ABC. We read ABC as a box product, okay. So these are the general properties of scalar triple product. A dot box product is B cross C is equal to B dot box product is C cross A is equal to C dot box product is A cross B. So these are the box product of ABC is equal to BCA is equal to CAB. Second one is IJK is equal to JKI is equal to KIJ is equal to 1 and IKJ is equal to minus 1. Third one is magnitude of the scalar triple product A dot B cross C of 3 vector is equal to the volume of a parallel pipe having sides A, B and C. Next is A dot A cross C is equal to 0. So box product is AAC is equal to 0. C dot A cross A is equal to 0. So CAA is equal to 0 is cross product. Next is if scalar triple product vanishes A dot B cross C is equal to 0, then A, B, C are coplanar. In that case volume of parallel pipe formed by them is 0, okay. Now scalar triple product. In scalar triple product, these are the figure of geometrical interpretations of scalar triple product. This is the square is OAB, okay. Angle of between A and N is alpha, okay, and this is OA, this is the OB and in middle OC, okay, and This OA is equal to capital A, OB is equal to capital B, OC is equal to capital C. So, B cross C is equal to BC sin theta into N. Okay. So, these are the equations of scalar triple product. This is a basic example. Now, thank you.